Hello, this is the solution set for AP Physics homework suggested problem set number 5.1. So we're beginning in chapter 6 with number 3 in the exercises. We have a worker who is pushing a 30 kilogram crate a distance of 4.5 meters along a floor at constant velocity by pushing horizontally on it. So let's draw a quick sketch of this. We have a crate on the floor. Person is pushing it, really long arms. The crate has a mass of 30 kilograms and it is pushed a distance of 4.5 meters. The coefficient of kinetic friction between the crate and the floor is 0.25. So we'll go ahead and say that mu k is 0.25. A asks, what magnitude of force must the worker apply? So we will start by sketching a free body diagram for this crate. So here's our crate. It has the force of gravity acting downward, which we can say is mg. It has some pushing force to the right. It has a normal force acting upward. And then it has a friction force to the left. And that friction force should be the same size as our pushing force as it moves at constant velocity. So, our application of Newton's second law in the x direction would give us push force minus force of friction equals ma in the x. And this acceleration is 0 since we're moving at constant velocity. So we can rewrite this as Fp minus mu k times the normal force is equal to 0. Next up, so we're looking for force push, so I'm going to go ahead and solve this for Fp. And so that would be, force push would be mu k times normal force. Then in our y direction, application of Newton's second law gives us normal force minus the force of gravity equals m times acceleration in the y, which is 0, as our box is not flying up into the air. So our normal force minus mg would be equal to 0, or our normal force in this instance is equal to mg. So I can substitute this right back into the equation I just found and say that force push is equal to mu k times m times g. And now I can substitute all of these values that I know. So mu is 0.25, our mass is 30 kilograms, and the gravitational field strength we'll go ahead and use is 9.8, and that's newtons per kilogram. So if we take these values and substitute them into our calculator, I find that the push force necessary is 73.5 newtons. So that is our answer to part A. Now B asks how much work is done on the crate by this force. So we'll go ahead and calculate the work done by the pushing force, and that would be equal to the force push times our displacement, which is going to be 4.5 meters. So substituting these values, we have 73.5 newtons times 4.5 meters. So our push work will simply be 330.75, so we'll just round that to 331 joules. Now C asks how much work is done on the crate by friction. So what we actually need to go ahead and apply here is to mention that in our previous instance of work calculation, we really should have included cosine of phi. And so for us, because our force and our displacement are in the same direction, so this is our displacement s, then the angle between these is 0. So this is, I'm sorry, not 0. Or actually, yeah, so the angle is 0, and so the cosine of it is 1. So when we go into C, we need to make sure we include this because the work done by friction is going to be the force of friction times the displacement times the cosine of the angle between the displacement and friction vectors. So this angle is actually 180 degrees. So what does that mean for us? That means when we calculate the work done by friction, we're going to have mu k times normal force times our displacement s times the cosine of our angle phi, and this angle phi is going to be 180 degrees. So when we substitute all of these values, we have 0.25, we have, actually we'll just say their normal force is mg. So let's actually erase that. So Fn, my normal force, becomes mass times acceleration due to gravity. And 30 kilograms times 9.8 newtons per kilogram times our displacement of 4.5 meters times the cosine of phi, which in this case is 180 degrees. So this right here is -1. So the work done by friction will be negative 73.5 joules. Oh, pardon me. That's times 4.5. So in fact, that would be negative 331 joules. So why does that make sense? Well, we're pushing at constant velocity. So according to the work energy theorem, any energy I'm putting in is not really being used to accelerate my object because its kinetic energy is not changing since velocity is constant. So I want to make a little footnote of that. Since v is a constant, that means that my kinetic energy is also constant. Therefore, the work done by the pushing force is going to be equal but opposite the work done by friction. So any energy I put in due to pushing is going to be immediately pulled out by friction. Now D says how much work is done on the crate by the normal force and by gravity. So this is quite simple to address because the work done by gravity and the work done by the normal force will just be the force of gravity times the cosine of the angle between these. So the force of gravity times displacement times the cosine of the angle between them. And this would be the normal force times displacement times the cosine of the angle between those. And so these angles, if we look at our diagram, are either 90 degrees or negative 90 degrees. So when I go ahead and substitute those in, that means that both of these cosines will be 0. The cosine of 90 or negative 90 is 0. Therefore, the work of gravity, or work done by gravity, is 0, and the work done by the normal force is also 0. Now, E asks, what is the total work done on the crate? Well, total work is just the sum of all of the individual components of work. So that would just be work done by the pushing force, plus work done by friction, plus work done by gravity, and work done by normal. Now, those two are 0, but we also see that work done by the pushing force is positive 331 joules, and work done by friction is negative 331 joules. So my total work is, in fact, 0. And again, this makes perfect sense because we do not have a change in kinetic energy overall for this box because it moves at a constant velocity. For question 6.4, we're using the exact same setup as the previous question or exercise. And so we have our box, but this time we're pushing downward on that box. So let's resketch this free body diagram. We have a downward force at an angle of 30 degrees below the horizontal. So that is our downward pushing force, and it is at 30 degrees with the horizontal. Now we still have a friction force that is parallel to our surface, so it is straight to the left. We still have a normal force acting upward, and we still have a force of gravity acting downward. And if we're paying really close attention, we should hopefully know that the normal force is actually going to be larger in magnitude than the force of gravity, because it must also work to counteract this pushing force that is acting somewhat in the negative direction. So, for part A, we're going to look at Newton's second law applied to our free body. In the x direction, we have the pushing force times the cosine of 30 degrees minus the force of friction is equal to ma in the x direction. And there is 0 acceleration because, again, we are wanting to move at constant velocity. So I can simplify this and say my push force times cosine of 30 minus mu k times normal force equals 0. And since I'm looking for the force the worker applies, I'm going to go ahead and solve this for Fp. So that would be equal to mu k times normal force over the cosine of 30 degrees. So now let's go ahead and find normal force using our application of Newton's second law in the y direction. In the y direction, we have normal force, and then we have minus Fg, and we also have minus Fp times the sine of 30 degrees. Now this is equal to ma in the y direction, so that is 0, as our box is not going through the ground. And so I'm going to try to substitute out this normal force here. So I'm going to solve for normal force eventually, but I can go one step here and say Fn minus mg minus Fp sine 30 is equal to 0. And solving for normal force, I have normal force is equal to mg plus Fp sine 30. And so I'm going to go ahead and substitute that in over here. So I actually regret having the cosine 30 there, so I'm going to go up one step now I think about it. So I'm actually going to go to this step here. So I have Fp cosine 30 degrees minus mu k times my normal force, which I'm substituting in to be mg plus Fp sine 30 degrees equals 0. So I'm going to solve this for Fp. So I'm going to distribute the negative sign to begin with. So I have Fp cosine 30 minus mu k times mg minus Fp sine 30 equals 0. So I'll do this one step at a time. So I have Fp cosine 30 degrees minus Fp sine of 30 degrees is equal to mu k times mg. Factor out the Fp, and I have Fp times cosine of 30 degrees minus sine of 30 degrees is equal to mu k times mg. So my pushing force will be equal to mu k times mg over the sum of the cosine of the difference between the cosine of 30 degrees and the sine of 30 degrees. So now I can substitute values. So my mu k is 0.25. My mass is still 30 kilograms. G still has a value of 9.8. All over the cosine of 30 degrees minus the sine of 30 degrees. So I'll get my calculator and plug these numbers in, and we'll see that the pushing force necessary is 84.4 newtons. So this should be higher than in the previous question because we are now pushing down on our box, which increases the force of friction resisting the motion. Now, we go back and we want to say how much work is done on the crate by this force when the crate is pushed a distance of 4.5 meters. So let's keep in mind that this force push is actually acting downward at an angle. So for part B, when I calculate the work done by the pushing force, I will have Fp times my displacement times the cosine of the angle between those two vectors. So my displacement vector is again in this direction, and the angle between these is, in fact, negative 30 degrees. So when I calculate the work here, I'm going to have my 84.4 newtons times my displacement of, again, 4.5 meters, times the cosine of negative 30 degrees. Now, it doesn't really matter if it's positive or negative because cosine is positive in both the first and second quadrants, but it will matter at some point, so let's be careful with that. And so we calculate this work done by the pushing force as 329 joules. Now, to continue on, C says how much work is done on the crate by friction during this displacement. So based off of our answer in the previous question, I think we can actually skip a few steps and note that constant velocity implies that the work done by the pushing force is equal to the negative of the work done by friction. Therefore, the work done by friction would be equal to negative 329 joules. Now, we can calculate that if we want. We can go back and find mu k times mg plus fp sine 30. But based off of our knowledge of the work energy theorem, we can skip a lot of steps. Now, D says, how much work is done on the crate by the normal force and by gravity? Again, we know that the angle between these two, so the work done by gravity, would be the force of gravity times S times the cosine of phi. And this cosine is going to be 0 for the force of gravity because phi is going to be negative 90 degrees. And for the work done by the normal force, the same thing occurs, just with a different force and a slightly different angle. And so that is 0 as well. And so the work done by each of these is 0 again. And then we say, what is the total work done on the crate? Well, we can skip again a few steps and just say that the total work is 0 joules, right? This comes from constant velocity. So there is no net change in velocity. So the work total is 0. For question 6.7, we have a linked mass system where we have two different blocks of different weights. Both blocks move at a constant speed, and both blocks move a distance of 75 centimeters. So the first thing I'm going to do is I'm going to do a little bit of unit conversion. I'm going to translate the 75 centimeters into meters, and so that will be 0.75 meters that the 20 Newton block moves to the right, and the 12 Newton block moves, we'll put it down here, 0.75 meters in the downward direction. So, the question asks, how much work is done on each block by each of the different forces that act on that block? So we're starting with the 12 Newton block for part A. So, the free body diagram for the 12 Newton block will have the force of gravity acting downward, and so we'll say that this is equal to 12 newtons. And we have a tension force acting in the upward direction. And those are the only two forces of note. Now, we don't necessarily know the tension yet, so we're just going to come back to that. In fact, I'm actually going to skip some space here and draw a free body diagram for the other block. So the second block has a force of gravity acting on it in the downward direction of 20 newtons. It has, in this case, a normal force acting in the upward direction, and it has a tension force acting to the right. And in order for there to be some amount of, in order for there to be a constant speed, the 20 Newton block must experience some friction in the opposite direction. So here are my two free body diagrams. And in order to go about figuring out how much work tension will do, I need to know what that tension force is. So this tension force will come from Newton's second law, and I'm going to start with the y direction because I know that normal force minus the force of gravity will be equal to mass times the y acceleration, which is 0. Therefore, the normal force will be equal to the force of gravity, or the normal force is equal to 20 newtons. Then, to go into the x direction, I will go ahead and say that the tension force is positive and the friction force is negative. And again, the reason I'm doing that is because I'm moving to the right, so I'm going to say that that's my displacement, and therefore that's my positive x direction. So in the x direction, my acceleration is 0, therefore tension force is equal to the force of friction. And I'm going to leave that there for a moment. And back to A, I know that my sum of forces in the y direction will be equal to I'm going to say force of gravity is positive minus the force of tension is equal to ma in the y direction, and the y direction acceleration 0. We're moving at a constant speed. Therefore, the force of gravity is equal to the force of tension, which is equal to 12 newtons. So again, I'm picking the downward direction to be positive because that is the direction of my displacement. So from here, I have enough information to find work done on this 12 Newton block. So the work done by gravity is going to be equal to the force of gravity times the displacement times the cosine of the angle between those two vectors. So the work done by gravity is going to be 12 newtons times my displacement of 0.75 meters times the cosine of, well, the angle between these two, as they're both going in the same direction, is 0. So the work done by gravity is just going to be 9 joules. 9 joules. Now, on to 2. How much work is done by the tension in the string? So the work done by tension is going to be equal to the force of tension times the displacement times the cosine of the angle between those vectors. So the angle between these two vectors is going to be 180 degrees. So when I go in and substitute, the work tension will be equal to my force of tension, which is 12 newtons, times my displacement of 0.75 meters, times the cosine of 180 degrees. So when I go through and calculate this, I should figure out that this is a negative 9 joules. And that's it for work done on the first block. Now for the second block, should start with 1, shouldn't I? We're looking at the work done by gravity. And so here, this is just for completeness sake, I have work done by gravity is force of gravity times displacement times the cosine of the angle between them. And so for work done by gravity, we have, in this case, 20 newtons times my displacement of 0.75 meters times the cosine of the angle between these two. And so that angle is going to be, here's my displacement vector, so that's going to be a negative 90 degrees. So my work done by gravity in this case will be 0 because the cosine of 90 or negative 90 is 0. So there is no work done by gravity in this case. And that makes sense because gravity is perpendicular to the displacement. Now, for the work done by tension, we have the force of tension times the displacement times the cosine of the angle between them. And so that will be, in this case, the same force of tension as before, 12 newtons, times 0.75 meters, times the cosine of the angle between those, and the cosine of the angle there is 0 degrees. So the work done by tension is going to be a positive 9 joules. And that's it for tension. 3 is friction, so I'm going to move over here so that I have room. So the work done by friction will be the force of friction times the displacement times the cosine of the angle between those. And so the angle between my displacement and my friction is negative 180 or 180. Either one's fine. And so this will be 12 newtons, which is from this right here, because I found the force of tension is 12 newtons above. So 12 newtons times 0.75 meters times the cosine of negative 180. And so the work done by friction here is going to be negative 9 joules. So we're starting to see a little pattern here. Then 4 says, what is the work done by the normal force? So the work done by the normal force will be the normal force times the displacement times the cosine of the angle between those. And so this is going to be 20 newtons times 0.75 meters times the cosine of 90 degrees. then my normal force is going to be 0 joules because the cosine of 90 is 0. So the total work done on each block is 0. So I'm going to write this right in the middle. So C, total work. Ooh, I don't like the red. Let's do purple. So the total work would be the sum of all of these works. But I can see that they are going to cancel out. And so the total work here is 0. And if you think about that, that's because there is no net change in kinetic energy. So there is no change in velocity overall, therefore the total work must be 0, according to our work energy theorem. For question 6.8, we have a grocery cart to which we apply a constant force given by this vector here. So I'm going to rewrite that. So this force is 30 I hat minus 40 j hat, and that's newtons. And the cart undergoes a displacement given by this vector s, and so that vector I'm going to rewrite as well. So that's negative 9 I hat minus 3 j hat, and this is in meters. And so how much work does the force you apply do on the grocery cart? So here I'm going to use my other definition of work. Work can be defined as the dot product of force and displacement. And so that's going to be the dot product of 30 I hat minus 40 j hat and negative 9 I hat minus 3 j hat. And so that's going to be newtons times meters in the end. So if you forget how to do a scalar dot product, you just multiply together the I components and then add that to the product of the j components. So that will turn out to be 30 times negative 9 plus negative 40 times negative 3. So the work done here will be negative 150, and newtons times meters is equal to a joule. So the work done is negative 150 joules. So if someone asks you what is this force actually doing, it appears to be slowing down a grocery cart. For number 611, we have a carton being pulled up a frictionless baggage ramp that is inclined at 30 degrees above the horizontal. So I'm going to go ahead and start sketching this. So we're going up a ramp, and the ramp is inclined at 30 degrees, and there is some kind of carton on it. So I'm assuming something like a milk carton. Maybe we'll even give it a little top like a milk carton. And is pulled up the ramp by a rope that exerts 72 newtons of force parallel to the surface. Now it also moves some distance, 5.2 up, or 5.2 meters up the ramp. So we have a 72 Newton force. We also have a weight. Let me make this a little straighter. So we have a weight of 128 newtons. And this right here is my force diagram. So I'm going to resketch this really quickly as a free body diagram. So I have 128 newtons acting downward. That's my force of gravity. I have 72 newtons acting up and to the right. And this is acting at 30 degrees to the horizontal. And there is a normal force that is up and to the left that is unknown. So the question, actually, let's go ahead and put our displacement in here as well. So our displacement goes this direction, 5.2 meters. So the question is, how are we going to tackle this problem? Well, I see that I have two forces that are at right angles to each other that are not aligned with my axes. So I'm going to go ahead and rotate my axis system so that those are lined up. So if I do that, my new set of axes will have an angle of 30 degrees right here. And my normal force and my tension are going to be on this set of axes. So since I'm moving in this direction, I'll say that's the positive x, and this is my positive y. So I'm going to need to find the normal force, so I'm going to go ahead and do my application of Newton's second law. So in the x direction, I'm just going to have my 72 newtons minus my 128 newtons times the sine of 30 degrees, which is equal to ma in the x direction. Now, do I know anything about acceleration in this case? I don't necessarily know, because there is no information here that tells me how much, or tells me anything about the velocity. So I'm going to go ahead and have to say I don't necessarily know. Now, what I will go ahead and point out is that I don't really need to do this because I know that the normal force is perpendicular to the surface. So this is worth noting, however, that I don't know anything about the acceleration of this object. In the y direction, I just have normal force minus 128 cosine 30 degrees is equal to ma(y). And I know this one is 0 because my cart is not, or my cartan is not necessarily accelerating. So this gives me enough information to find normal force. So my normal force is going to be 128 times the cosine of 30 degrees. And that gives you a value of 110.85, or let's just say 111, and that's newtons. So now we can go ahead and start answering our questions about work. So A says, what is the work done by the rope? So this is going to be the force in the rope times the displacement times the cosine of the angle between them. And the angle between the displacement and the force in the rope is 0. So the work done by the rope is going to be 72 newtons times 5.2 meters times the cosine of 0 degrees. And so the work done by the rope here is 374, I'm not going to round this actually, it's 374.4 joules. Now B says, what is the work done by gravity? So the work done by gravity is going to be the force of gravity times the displacement times the cosine of the angle between them. Now the angle between these is going to be this angle here. And this angle is going to be 120 degrees, or more specifically, negative 120 degrees. So this negative 120 goes into my cosine. And so the work done by gravity is going to be 128 newtons times 5.2 meters times the cosine of negative 120 degrees. So the work done by gravity will end up being negative 332.8 joules. Apologize for that weird 8. C says, what about the work done by the normal force? Well, the work done by the normal force is going to be the normal force times the displacement times the cosine of the angle between them. And the angle between these two forces is 90 degrees or negative 90 degrees, whichever. And so when I go in and plug this in, I don't necessarily need to know the normal force to know that the cosine of 90 degrees is 0. Therefore, the work done by the normal force is 0. Now D says, what is the net work done on the carton? So here we can go ahead and calculate the net work as the sum of all of these works. So work done by the rope, work done by gravity, work done by normal force, such as it is. So that will be positive 374.4 minus 332.8, and this will be in joules, plus 0. So my net work is going to be 41.6 joules. Now, E says, suppose that the rope is angled at 50 degrees of being above the horizontal. So, what's going to change? So, instead of having this angle of 30 degrees, I'm going to have an angle of 50 degrees with the horizontal. So here's my rope force of 72 newtons. This is an angle of 50 degrees. And my displacement vector is actually still in this direction. So this is still 30 degrees. So when I go and calculate the work done by the rope, that's going to be still the force of the rope times the displacement times the cosine of the angle between them. And so my rope force has not changed. My displacement has not changed. It's still 5.2 meters. The angle between them, however, has changed. So this new angle is going to be from the displacement vector to the force, and that is going to be a positive 20 degrees. So I will put that in as my angle, and my new work done by the rope will be 352. We'll go ahead and round this one. 352 joules. And so that's less work than before because not all of the force from the rope is going toward doing work. For question 616, we have a 1.5 kilogram book sliding along a rough horizontal surface. So here's my book. It has some pages. And it is on a surface. At point A, so VA, it is moving at 3.21 meters per second. And then at point B, sometime later, it has slowed to 1.25 meters per second. So A asks us how much work was done on the book between A and B. So since we're given, I should include my mass, information about the velocity of the object, and we are asked about work done, then we are going to be using the work kinetic energy theorem. So the work would be equal to the change in the kinetic energy of this object. So, make this a capital K. That work we can rewrite here as 1/2 the mass times velocity. Actually, let's back this up. Since this is changing kinetic energy, that would be K2 minus K1, which we can rewrite as 1/2 times the mass times the square of the final velocity minus 1/2 times the mass of the square, or times the square of the initial velocity. Now, I can rewrite this as both include the same mass and the 1/2 as 1/2 mass times the square of the final velocity minus the square of the initial velocity. So the work done on the book must be equal to 1/2 times 1.5 kilograms times the square of 3.21 meters per second minus the square of 1.25 meters per second. So my work will end up being positive 6.56, we will round, joules. Now B says, if negative 7.5 joules of work is done on the book from B to C, how fast is it moving at point C? So we'll say there's some VC later, and in between these two, we have a work value of negative 0.75 joules. So here I'm going to use, again, my work energy theorem. I'm going to say that this is work AB. And so my work BC is going to be equal again to the change in kinetic energy. But I'm going to be a little more specific. I'm going to say that this is going to be KC minus KB. In fact, I might even go back up here and rewrite this as A and B. So this would be KB minus KA. This would be velocity B minus velocity A, velocity B, velocity A. So the work done from B to C, we know the value for, and I know that the kinetic energy here will be 1/2 mass times Vc squared minus 1/2 mass times Vb squared. Now I'm looking for Vc, so I'm going to go ahead and rearrange this equation. So what happens? Well, we're going to have Vc squared, I'll do this in 2 steps. 1/2 mass times Vc squared is equal to the sum of the work done, Bc, from B to C, and the mass times velocity b squared. And so if I'm looking for Vc, then that would be the square root of, so we're going to be dividing by 1/2 m, so that would be 2 over m times work done from B to C plus 1/2 mass times Vb squared, all in a radical. So I'm going to substitute values now. So this is going to be 2 over 1.5 kilograms times my negative 0.75 joules plus 1/2 times 1.5 times my velocity at B, which was 1.25 meters per second, squared, and then square root all of that. So putting this into my calculator, I'm going to get the value for Vc to be a nice round 0.75 meters per second. Now question C asks, how fast would it be moving if 0.75 joules of work was done from B to C? So now the same, since I've solved this already for Vc, and I just want to use a different work, I can actually just take this symbolic equation that I found and use a different value. So I'm going to be using work Bc is positive 7.5 now. So that will give me, if I substitute all of this in, Vc is equal to 2 over 1.5 times positive 0.75 plus 1/2 times 1.5 times the square of 1.25, all in a square root. And so we go ahead and calculate this, and I get a velocity of positive 1.6 meters per second. So that makes sense. If we have positive work, then that means our velocity is increasing because our kinetic energy should be increasing. We're adding energy to the book. For the negative work, we were taking energy out, so our velocity should decrease. And that's all there is to this problem. For question 620, we have a 4.8 kilogram watermelon dropped from rest from the roof of an 18-meter tall building. So let's do a quick sketch. Here's a building. It's 18 meters tall to the ground. And here is our watermelon. Ooh, let's make it green. Here's our watermelon. And our watermelon has a 4.8 kilogram mass. And so A asks us, what is the work done by gravity on the watermelon during its displacement from the roof to the ground? So my displacement is this 18 meters in the downward direction. And so when I go in and calculate the work done by gravity, I will have the force of gravity times the displacement times the cosine of the angle between these. So that will be 4.8 kilograms. Oh, I should, I guess, point out, in case you've forgotten, force of gravity is equal to mg. So that will be 4.8 kilograms times, I'm going to go ahead and use 9.8 newtons per kilogram because I'm using a calculator, times the cosine of 0 degrees as they are acting in the same direction. Right? So the free body diagram for this will just be force of gravity in the downward direction. So the work done by gravity here will end up being simply 44.1 joules. Now, that is positive because because the force of gravity and the displacement are in the same direction. Now, B asks us, just before it strikes the ground, what is the watermelon's kinetic energy? So, from the work kinetic energy theorem, I know that the work is going to be equal to the change in kinetic energy, or in this case, K2 minus K1. And I know that K2 will be 1/2 mv2 squared, and K1 will be 1/2 mv1 squared. Now, since I start at rest, V1 is equal to 0. So this whole term is 0. Therefore, my work will be just equal to 1/2 mass times the square of my final velocity. So I can do a couple things here. I can go ahead and say that since this term is 0, K1 is 0, so my work will just in fact be equal to K2. Or, in this case, K2 will be equal to 44.1 joules. And so this right here is part 1. Part 2 comes from the same work, or the same setup, where we can say that if I solve this for V2, I would have V2 is equal to 2 times the work over the mass square rooted. So V2 will end up being the square root of 2 times 44.1 joules over my mass of 4.8 kilograms square rooted. And that velocity will be 4.29 meters per second. Or I'm sorry, this should be speed, I will say. So there is no direction attached to it right now. Now C says, which of these from A and B would be different if there were appreciable air resistance? So this is just a conceptual understanding. So the question is, would the work of gravity change? The answer is no. Fg doesn't change. The force of gravity does not change. And neither does the overall displacement. So the work done by gravity is not going to change. So the work done by gravity does not change. Now B asks us, does the kinetic energy change and or does the speed change? Because as we see, if one of these changes, then the other should change. So for this, it's a little trickier, because even though work of gravity does not change, we actually are adding a work done by the air resistance, right? It is a frictional force. And that force will be acting upward against our displacement. So that means that our work done by the air will be negative. Therefore, our kinetic energy should be reduced. It should be lower, because now you have the air that is pulling some energy out of our object, assuming it doesn't get to terminal velocity. So if K2 is lower, then the velocity 2 should also be reduced. For question 631, we have a car traveling on a level road with a speed V0 at the instant when the brakes lock, so when you hit the brakes, so that the tires will slide rather than roll. And we want to use the work energy theorem to calculate the minimum stopping distance of the car in terms of V0, G, and the coefficient of friction, mu K. So let's go ahead and sketch what's going on here. Here's my car. It's terrible. We have a road. We have a V0 to the right. We have some displacement. And we'll say that this is, let's just give it an S. And so we're looking for S in this case. So the work kinetic energy theorem says work is equal to change in kinetic energy. Now let's go a little bit further than this, and let's say that it is also equal to the force that is causing or doing the work times the displacement. So go ahead and rearrange this, and we see that the displacement will be the change in kinetic energy over the force that is doing this work. So what force is doing the work? Well, if I resketch this as a free body, I have force of gravity acting downward, not doing any work. A normal force acting up, also not really doing much work. Then I have simply a force of friction acting to the left to slow this car down. And that's all we have. So Newton's second law will give me two things. In the y direction, it will give me that normal force minus the force of gravity is equal to ma in the y, which is 0. So my normal force is equal to the force of gravity, or with symbols, the normal force will be equal to mg. Then in the x direction, I just have force of friction is equal to ma in the x, and that is non-zero. So I'm just going to leave that as is for right now. I could go one step further and say that this is mu k times normal force in the negative direction. How about that? Is equal to ma in the x direction. So let's go back to my work. So I've solved for this displacement already. I'm going to go ahead and expand my delta k to be k final minus k naught over the force now of friction. So what I can do is a couple simplifications. The first is I can say that k is going to be 0. So I can say that because k is 1/2 times m times v squared. And v final is going to be 0 because we're going to stop. Therefore, k is going to be 0. So this simplifies to just be negative k naught over the force of friction. Now, my force of friction is actually going to be negative, but we're not quite to that point. So I'm going to go to the next step. So my k naught is going to be negative 1/2 m times v naught squared. And my force of friction is going to be negative mu k times my normal force, which I can go ahead and rewrite as negative mu k times now mg. So what I see ends up happening here is mass cancels and negative signs cancel. And so I'm going to move my 1/2 to a 2 in the denominator. And so my displacement will just be v naught squared over 2 times mu times g. Now B says, by what factor would the minimum stopping distance change if the coefficient of kinetic friction were doubled? So let's go ahead and start B here. So if mu k doubles, what happens to the stopping distance? So if I plug in a 2 mu k in my denominator, I end up having the stopping distance. So S halves or a 0.5 factor. You can think of it as either. And the reason for that, which makes perfect sense, is if my coefficient of friction is higher, that means I have a larger friction force. So I'm going to have a shorter stopping distance. So this is 1. Now part 2 says, what happens if the initial speed is doubled? Okay, so if v naught doubles, so if I plug in 2 times v naught here, which I can go ahead and write, my S would be equal to 2 times v naught squared over 2 mu kg. I see what ends up happening is I get a 4 that pops out times v naught squared over 2 mu g. And so this 4 times my original stopping distance means that S quadruples, or a factor of 4. Because I have a much higher speed, so I need a much greater stopping distance. And then finally, 3 says, what if both were doubled? So if v naught and mu k are doubled, what happens? So I have S equals 2 v naught squared over 2 times 2 mu k times g. And so I end up with a situation where I have a 4 and a 2 that pop out times my initial expression for stopping distance. And so all we get here is S ends up doubling. So that's a factor of 2. And so all you need to do in order to figure out what happens to my stopping distance is take my symbolic expression and plug in either a double or a half. And you can figure out what ends up happening as a function of my original expression.